For chapter 24, we're specifically going to focus on the physiological responses to altitude. So we're going to talk about which environmental conditions constitute altitude, the various physiological responses to acute or short exposure to altitude, exercise and sport performance at altitude, how do you acclimate to altitude with chronic exposure, ways that you can use altitude to optimize performance and training, and then some of the health risks due to exposure to altitude. So the first thing to cover is a bit of terminology. And so the first piece of terminology we need to consider is the barometric pressure, which is abbreviated with a large P and a small b. And this is the measure of the total pressure that all the gases composing the atmosphere exert on the body. And importantly, if you think about a jug with the molecules that make up the air, so you have your oxygen, your nitrogen, and your carbon dioxide. All those molecules are bouncing off of each other. So they're putting some sort of pressure on whatever else is inside that jug. Well, now let's say instead of a jug, it's Neyland Stadium, but you have the same number of particles that you initially had in that jug. If you expand the volume to be something very large like Neyland Stadium, now those molecules are not going to bounce off of each other very often or any other body that would be standing in Neyland Stadium. So that would be a decrease in barometric pressure. And that's how it works when we go to altitude. We see that barometric pressure will go down because the molecules themselves in the air are bouncing off each other less often. And so we've studied this concept specifically talking about partial pressure. And when we're talking about partial pressure, we're zoning in on one type of gas molecule. So often we're most concerned with the oxygen molecules because that's what we need to undergo metabolism. And so we know that the percentages of gas don't change in the air as you change in altitude and then barometric pressure changes, but rather that the partial pressure changes. And we went through those calculations in previous chapters in the respiratory chapter, but we'll also look at those numbers again when we're talking about specific types of altitude. Some other terms that are important to note if we're looking on the left-hand side, the word hypoxia means low partial pressure of oxygen, and we see this at altitude. Normoxia would be a normal partial pressure of oxygen at sea level, and that's 159 millimeters of mercury. And if you're wondering, how did I calculate that without seeing anything? It's because I know that barometric pressure at sea level is 760 millimeters of mercury. And if I take 760 and I simply multiply by the percent of oxygen in the air, which is 20.9%, I'll get approximately 159 millimeters of mercury. Hyperoxia would be when you have very high partial pressures of oxygen, and you can do this artificially using a gas tank. We have hypobaric, which would be reduced barometric pressure at altitude. Again, we have the word hypoxia, and I've put this a second time because sometimes we use this phrase just referring to low partial pressure, but specifically hypoxia is referring to low partial pressure in the air, whereas we would use the word hypoxemia to refer to low partial pressure of oxygen in the blood. So these two terms on the lower right-hand side, just make sure you're differentiating between the two of these because technically one term is describing partial pressure in the blood, whereas the other hypoxia is determining or defining partial pressure of oxygen in the air. So at altitudes that are less than 1,500 meters, we wouldn't expect there really to be any physiological effects of altitude. We'd consider these basically sea level. So Miami, Florida is a great example of a city that's at sea level. So that means the barometric pressure is 760 millimeters of mercury. So we have roughly 20.9% oxygen. That'll give us a partial pressure of oxygen of about 159 millimeters of mercury. Another thing to note here is that the average temperature in Miami, Florida is roughly 60 degrees. So let's jump up to an altitude where there's actually some significance to that altitude. So Denver, Colorado is a great example. They sometimes call this the Mile High City. So at this point, we're at an altitude of 1,600 meters. So this means our barometric pressure has gone down to about 630 millimeters of mercury, which means our partial pressure of oxygen has also gone down to about 132 millimeters of mercury. So as we go up in altitude, that barometric pressure as well as the partial pressure of the gas is going down. Notice also that the average temperature in Denver, Colorado throughout the year is about 47 degrees Fahrenheit. As we continue our journey up in altitude, we reach Mexico City. Mexico City sits just above 2,000 meters, so about 2,200 meters. The barometric pressure is about 585 millimeters of mercury. Why is Mexico City relevant? Well, in 1968, the Olympics were actually held in Mexico City. And this was one of the first times that individuals in different countries specifically started getting excited and curious about how that high altitude would impact the various athletic events during the Olympics. So would it be helpful or would it be a hindrance depending on what the event is? And we'll talk about that a little bit later as we move through this chapter. Now, because that barometric pressure has continued to go down, the partial pressure of oxygen has dropped to about 122 millimeters of mercury. Also notice that the average temperature in Mexico City throughout the year has dropped to about 36 degrees Fahrenheit. As we continue our climb in altitude, we're jumping back over to Colorado, and specifically one of the famous peaks, which is Pikes Peak, which is in Colorado Springs. So Pikes Peak is what's known as a 14er, meaning it sits at or slightly above 14,000 feet. However, when we look at that in terms of meters, that's about 4,300 meters. The barometric pressure in this case is 430 millimeters of mercury, which means our partial pressure of oxygen has dropped all the way down to 90 millimeters of mercury. Not to mention the temperature. We're starting to get into some really cold temperatures as we ascend to altitude. The average temperature on the top of Pikes Peak is just 12 degrees Fahrenheit throughout the year. Now everybody knows the name of this last peak, which is Mount Everest, an iconic climb for most alpinists. Mount Everest sits at 29,000 feet, which is roughly just over 8,000 meters. And it is quite a feat to be able to climb Mount Everest without using any supplemental oxygen. Why is that such a feat? The barometric pressure at the top of Mount Everest is down to 253 millimeters of mercury, which means our partial pressure of oxygen is just 53 millimeters of mercury. Now, if you're thinking back to respiratory physiology, you should remember that the partial pressure of oxygen within the muscle is just 40 millimeters of mercury. So we've just significantly decreased that gradient from going from outside in the atmospheric air to down to getting that oxygen to our tissues, which is going to make it really problematic for delivering that oxygen. Not to mention the cold, cold temperatures on the top of Everest. You're going to want to bring your warmest jacket. The average temperature on top of Everest is negative 46 degrees Fahrenheit. So what's the important common thread that we just saw? We saw that as we increase in altitude, that barometric pressure is going to go down, which is going to lead then to a decrease in the partial pressure of oxygen as well as all of our gases, which will affect our ability to bring oxygen from the air and get that to our exercising tissues. Of important note as well is that the typical temperature is going to go down as we go up in altitude. So we also have a cold stress as we go up. So as we mentioned, as we go up in altitude, air temperature is going to go down. As we ascend every 150 meters, we'll see a decrease in the average temperature of about 1 degree Celsius. So one concern we have for people who are climbing at high altitudes are any of our cold-related disorders. And I'm specifically thinking of something like frostbite for any cold exposed skin. The other challenging aspect as someone ascends in altitude is the humidity of the air. Cold air does not hold very much water, so that air becomes very cold as well as very dry. And dry air is going to lead to faster dehydration via both the skin as well as the lungs. So it is vital that individuals are taking in ample amounts of water whenever they're climbing at these very high altitudes to try and prevent dehydration and some of the performance deficits that we have with dehydration. We already know they're going to have performance deficits from going up to altitude, so we don't want these to be compounding factors. You also have to be more concerned with solar radiation as you go higher in altitude, primarily because there's less atmosphere that UV rays have to travel through as you go up in altitude. So it's really common to see people climbing high peaks wearing a lot of sunscreen and wearing sunglasses, because in this case they've got the snow reflecting off, or sorry, you've got the light reflecting off of the snow, not to mention just less atmosphere that the UV rays are traveling through, so they need to protect their eyes and particularly protect their skin from any sort of significant sunburn. When you go to altitude for the first time, even if it's lower altitude, something like Denver, where you're only a mile high, you're going to notice one thing that's going to happen first. And for everybody, this is a little bit different as to how exaggerated that first response is going to be. But the first thing, if you're paying close attention, that you'll notice is that your ventilation is increased upon arriving at higher altitude. And so you'll notice this at rest and at submaximal exercise. You won't notice this at maximal exercise, so it doesn't somehow increase your overall possible ventilation. But for any given intensity of exercise, or in this case rest, ventilation is going to be a little bit higher. And the reason that ventilation is going to be a little bit higher is because that partial pressure of oxygen being lower is stimulating the chemoreceptors that exist in your carotid arch and your aortic arch. And so that's going to stimulate a higher respiration rate in this case. And that will persist for several days. In some cases, it's just for several hours. It really depends on the individual and what their responses look like to that level of altitude. Again, lower altitude is going to elicit a smaller response. If you were to jump up to much higher altitude, you're going to get a more robust response in this case. So because of this increase in ventilation, someone is basically in this case, they're hyperventilating. And so just like whenever someone hyperventilates to hold their breath longer, if they're hyperventilating, they're decreasing the partial pressure of CO2 at the level of the lungs. And so that's going to allow them to increase the CO2 gradient and blow off more CO2. And that's going to put someone in a respiratory alkalosis. So remember, if we're blowing off CO2, then we're also getting rid of hydrogen ions as we're transporting those hydrogen ions and CO2 out of the blood. So our blood is becoming less acidic, meaning it's becoming alkalosis or alkalytic, so more basic. And it's doing so because of elevated respiration, which is why we call it respiratory alkalosis. So this very fast response actually drives us to have a higher pH. And that higher pH is going to lead to a shift to the left in our oxyhemoglobin dissociation curve. And that curve shifts to the left, which is going to result in a longer loading phase of oxygen with hemoglobin to try and prevent any additional hyperventilation from occurring, because you wouldn't want your ventilation to just continue to increase. That would impact your ability to do any exercise at that altitude. We do have a slower response that starts to kick in a couple days after exposure to high altitude, and that's actually going to come from the kidneys. And our kidneys are actually going to excrete more bicarbonate in this case. And now that will minimize the blood buffering capacity of our blood, because normally bicarbonate is going to bind those hydrogen ions, and it's going to be how we're transporting those hydrogens out of the blood. But this is going to allow us to reverse that alkalosis and return our blood to a much more normal pH. So our kidneys are really important for this longer, slower response to altitude exposure in maintaining blood pH.